Now in this second part of the lecture, we will prove very fundamental result which is used very often for a computation in determinants, and besides that it is also interesting in its own right that it is what is called a product formula. So, we now come to, we will prove the fundamental product formula. For determinants. And also we will use this product formula for the computation of inverse also. So, this is used very often. So, what do you want to prove? I want to prove that if I have two square matrices A and B of the same order, then determinant of the product equal to product of the determinants. Okay. So, proof. I will use the fact that this determinant function is alternating and n multilinear. Okay. So, let us denote, let x1 to xn be the columns of B. Then A x1, A xn, these are columns of the product. AB. That is how the matrix multiplication is defined. And now consider the map. Let me call it F. This is from k power n cross k power n. Remember, this is n times. This is nothing but m n k. Columns. So, what is the map? And from here to the scalars, what is the map? Take any matrix B and map it to delta E. Delta E is the standard determinant functions on k power n, and map these two, evaluate at these columns A x1, A xn. This makes sense. This is a map from k n n times to k or m n k to k. This is the map defined. First thing I want to check that this map is alternating n multilinear. First let me check multilinearity. Multilinearity in each variable. But you see, if I change this matrix B, so let me write formula. So okay, because this in each variable this is linear, therefore it is multilinear. To check it is alternating, I have to check that if two components are equal, then they are equal. Two components are equal if B, so this This is clearly alternating and multilinearity. So, I will just simply say check yourself, there is nothing much to check. So, therefore, if it is alternating, then what is the so this is by definition, this is nothing but determinant of A times B, because these are precisely the columns of A times B, and then this is a standard determinant function. So, this is determinant of A times B. So, determinant of A times B, this is f of the matrix B, that is the definition of f of B, and this is f of x1 to xn, they are columns of B. But we have seen that any alternating n multilinear map is a scalar multiple of the standard determinant function, because this ALT n k power n, this is one dimensional, and this standard determinant function is a non-zero element in this. Therefore, this non-zero element will be a basis of this vector space, which is one dimensional, and f is one of them. Therefore, f has to be a scalar multiple of delta E, and which scalar multiple, that we also know how to do it. This is delta E of x1 to xn times f of E1 to En. This scalar is precisely the determinant of B, and this one is by definition determinant of A. Remember, this is by definition E1 to En are the columns. So, this is B is E1 to En, that is B is identity. So, this is determinant of A. So, that proves. So, you see, this proof is not very difficult, but it depends. It is easy because we know this vector space is one dimensional, and the main theorem of determinant theory says that there is a standard determinant function, and therefore, every other alternating multilinear map is a scalar multiple of that, and we know how to calculate by using the properties of alternating multilinear maps. Okay. So, that proves the product formula. Now, suppose A, the square matrix A is invertible. If A is invertible matrix, remember our notation that set of invertible matrices or set of inverses in this ring, MnK is a ring, it is non-commutative, but the inverses in this ring, that is inverses here, that is this is our notation, and this is precisely we are denoting GLNK, and this is clearly a group because it is invertible elements in a multiplicative monoid, and it is a group. This group is also called general nth general linear group. This is very important group even in other branches of mathematics, analysis and Lie algebras, Lie groups, etc., so on. So, if it is invertible, then I know there exists an inverse. So, that is there exists a inverse in Mnk with the property that A times A inverse equal to identity, also equal to A inverse times A. Such a inverse is unique, and we need to write down both the conditions in the definition, but we have checked in our using the theory of finite dimensional vector spaces, one equality is enough to conclude the other also, because linear maps which are injective or surjective, and bijective, surjective, injective, they are all equivalent, and these I keep calling a pigeonhole principle in linear algebra. Anyway, so we have this. So when you apply determinant on both sides, we get determinant of the product equal to determinant of the identity matrix, and determinant of the identity matrix is obviously 1, because if you want to formally say it, it is a upper triangular matrix with 1 1 on the diagonals, and we have just put the 1 1 on the diagonal, the product of 1 1 is 1. So on the other hand, this product is the product of the determinants. Therefore, altogether this is equation in the field now. Therefore, we get a nice formula, determinant of A inverse equal to determinant A inverse. So that means if your matrix is invertible, whether you apply inverse first and then the determinant, or determinant first and the inverse, these two operations are compatible. Okay. So moreover, also think of, so a determinant gives a map therefore from GLNK to K cross. Any A goes to determinant A. We have noted invertible matrix cannot have 0 determinant, because the product is 1, and if one of them is, determinant is 0, product cannot be 1. We are in a field, that is important, and the product formula tells you this is actually a group homomorphism. And whenever you have a group homomorphism, then you can talk about the kernel, image, isomorphism theorems and so on. So let us see in this case, first of all, this map is surjective, I say. 1, this det map is surjective. So what do I need? Given any scalar, I want to find a determinant whose find a matrix, invertible matrix whose determinant is that. So given a non-zero scalar, look at the matrix, n is fixed. Look at the matrix, you put A on the top entry on the main diagonal and put remaining entries to be 1 1 1s, and then this is the special matrix. The determinant of this matrix is obviously the product of the product of the diagonal matrix, which is A. So therefore, A is in the image of this map. So that is the determinant map is surjective. Secondly, what is the kernel of this determinant map? Kernel of this determinant map is a very important group, which is the set of all matrices, invertible matrices, such that it goes to identity. Remember, identity in this K cross group is 1. So that means all those invertible matrices whose determinant is 1. This is a special group, therefore it has a special notation and special name. It is called a special linear group, SLNK. This is special linear group, special linear group. Always over K. So remember this, when K is a finite field, then the GLNK is a finite group, and in this case it will be interesting to compute its order and other invariants of the group, which I will not do it in this course. Similarly for SLN and so on. So we know the kernel, we know it is surjective, therefore we can also apply isomorphism theorem. It will say that GLN mod the kernel, because its SLNK is the kernel of a group homomorphism, it is a normal subgroup, therefore this quotient makes sense. This is a quotient group and this group is isomorphic to its image, but image is everybody. So, this is K cross. So, this is a group isomorphism. Okay. Okay, now I want to recall, let me write as an example. This is what we have done it in when we studied elementary matrices. So, I will just summarize in this example with this new language what we have done in that. So, remember if you have given an invertible matrix A over a field, we have by using elementary operations on A, elementary operation means row, column and all those operations. We have written this A, so we can write A as a product of a diagonal matrix diag D 1 1 1 1 1 and elementary matrices. So, let me write A, we can write A as a product of the diagonal matrix and elementary matrices B, I, J, A, where I is not J and A is in K. This we did it very carefully in that elementary matrices product. See, normally you get the diagonal matrix, but then we have shifted the diagonal entries successively to the upper position and we brought this to the top position. Now, because the determinants of this elementary matrices is 1 and when A is the product of this and this D, this entry D is nothing but the determinant of A. And if this original matrix were having determinant 1, then actually this is identity matrix. So, you will not require this. So, that shows two very important observations which I want to say in terms of group theory. So, this means the group GLN A is generated by these elementary matrices and this type of diagonal matrix generated by that, because every matrix, every element in GLN we have written a product of this. So, therefore, the matrix GLN is generated by this type of diagonal matrices and the elementary matrices of, these are elementary matrices of special type, they are not elementary matrices, they are the one of type 2 I think in that notation. So, this is very important when, for example, when you prove, so it is finitely generated in particular, not finitely generated, these matrices are not finitely many in number unless the field is finite. So, if field is finite, K is finite, then they are actually finitely and you know the generators also very specifically. And SLNK is also generated, now you do not need this. So, SLNK is generated by these elementary matrices. So, for example, when you want to prove when K is in a classical case, K equal to R for example, and if you want to prove results about GLN R or SLN R, and similarly for GLNC and SLNC. Suppose, so in this particular case these groups are not just groups, they also have topology which will inherited by the usual topology of Rn or Cn, and these are, even the group operations are continuous, that means these are Lie groups. And if you want to prove, for example, GLNC is connected, you use this statement which will be very neat to check that GLNC is connected, because you connect only elementary matrices, and if once you connect the generator, then the all elements will be connected, path connected and so on. So, this is very important when you study what is called classical groups. Okay, that with that I will not make more comments in this. Okay, so the next is now we can write more results about these group theoretic results, but I will not do that. For next one also one could describe the center of this group and so on, and their quotient groups and so on, but I will not do it in this course. Orders and so on, and its connection with the other finite groups, which I will not do it now. But now I will concentrate on finding the inverse, finding the inverses of a given invertible matrices. So, these are the computational problems. How do we find the inverse of a given matrix A? So, A is a matrix given, and we also know for sure that it is invertible. And how do we check that? For this, checking is easy. We just compute the determinant of A and check determinant of A is non-zero. That means it is an element in K cross, and we know that if determinant is non-zero, then the matrix is invertible. This we already noted earlier. So, having noted this, first thing we have to note this, and then we want to write the inverse explicitly in terms of the entries of A. And for this, what we need is what is called adjoint determinant, adjoint of a matrix, and the relation between adjoint and the original matrix. So, this which I will call it adjoint determinant formula. So, these two topics, first I will spend some time to define adjoint and then prove the adjoint determinant formula. Actually, it will also be not a bad idea to do it like what we did it for the functions first or for the linear maps first, and then prove the formulas for that, but I will do it this time with the coordinates. So, I am now preparing to define adjoint of a matrix. So, start with the matrix A. The adjoint of a matrix is always defined. So, start with the matrix A is Aij. This is n cross, it is a square matrix. For adjoint is defined for a square matrix. So, start with the matrix, and what do I do is I fix the ijth entry. So, fix ijth entry. That means I fix ith column and ith row and jth column. So, and from the matrix A, I remove ith row and jth column. So, that means what? And the notation is I will now use 1, ith row is here and nth. These are all rows, and I will put a cap on I. This means I have removed ith row. Similarly, for 1 j, I have removed jth column. So, I got n minus 1 rows and n minus 1 column. So, I got a square matrix of order. So, this is a matrix in M n minus 1 k. Sometimes, so the determinant makes sense. So, the determinant of this matrix, so determinant of this matrix A 1 I this n 1 j, this is some scalar. This scalar I am denoting by capital A I j. It depends on I, it depends on j, and it is some scalar. If I want to write this scalar as a determinant of 1, so this is also can be thought as keep the same thing. I want to make it, so I will write a formula and then check. So, this is Aij is also determinant of course keep this matrix, and I want to enlarge it to n cross n matrix by adding a row and a column. So, I add the first column, I add it as the first column. First column is 1 0 0 0, and here I add the ith, I put in the ith row on top here, but only the entries from these columns. So, that means I am adding this row as A I 1 etc., etc. Obviously, I will omit the entry Aij and then keep Ai n. Note that this is ith row, except I have not taken the jth column. Instead of that, I put this column, and here is the matrix A, this matrix. So, now note this equality is clear, because I will expand in terms of this first row. When I expand in terms of the first row, it is 1 times this determinant, which is this. And if I want to bring this now in the middle at the jth row, this first column, if I want to bring it as a jth column, and this entry 1 I want to bring it at the jth ith row, then what do I have to do? I have to interchange rows and columns, and if you notice, I have to change I minus 1 interchanges of rows and j minus 1 interchanges of the columns. So, this will all together be minus 1 minus 1 power I plus j, and then the matrix obtained from A by removing the jth column to be just 1 at ijth place and 0 everywhere else. So, this is precisely the determinant of, I will write only the jth column, that is 0 0 0 1 0 0, this is the jth column, and remaining entries are like matrix A. So, this is called the ijth cofactor. So, remember, note the sign. The sign is very important to note. And how did we get this? We got this because what happened? This sign is we got it by interchanging ith row successively, I minus 1 interchanges of this row, and each time you will get minus 1 sign. So, minus 1 power I minus j will come from row changes, and then again change it to jth column. So, that means I minus 1 changes j minus 1 changes of the column. So, this will be this sign. So, altogether it will be, see, minus 1 minus 2, that will even, so it will disappear and then it is same as this. So, this is called this capital Aij is called ijth cofactor of the matrix A. And note that because of that, this Aij, which is just now I said minus 1 power I plus j and times what? So, I want to write, yes, precisely, I want to write this determinant. So, what are the columns? Columns are the original columns of A and only this column is changed. So, that is delta with the standard determinant function, then x1 xi minus 1, and here it is ei, next is xi plus 1 to xn, where x1 to xn are columns of A. All right. So, and the matrix, now I take transpose of this matrix. So, I will take Aij. So, let me define entries A small suffix Aij tilde, this is by definition minus 1 power I plus j and then capital A ji. Note the change in the indices. This matrix Aij tilde, this matrix, this is a matrix n cross n matrix, and this matrix is called the adjoint of A. So, the notation is ADJ. This is called adjoint of the matrix A. And now next time I will prove so called adjoint determinant formula, and essentially we will prove that this adjoint matrix will help us in computing the inverse of a matrix when A is invertible. So, thank you.